Hi everyone, welcome to the video lecture on nonlinear models or nonlinear programming, the short form NLP, which is going to be used throughout this module. So for this week's module, we're going to continue with chapter 6, and this is the last topic from chapter 6. So far in chapter 6, we've covered integer programming, IP, and goal programming GP models. So far in all the three types of models that we've covered, LP, IP, and GP, all of them assume that a problem's objective function and constraints are linear. That means that they cannot contain nonlinear terms such as x to the power 2 or x to the power 3 or 1 divided by x, the log of x, or 4 multiplied by x multiplied by y. So all of these are examples of nonlinear terms that you may add to your mathematical model. However, in a lot of real world situations, the objective function or one or more of the constraints may be linear, and this is not a very unrealistic assumption to make that relationships across variables are nonlinear. We see all the time that relationships cannot be perfectly drawn on a straight line. In that case, they are definitely nonlinear, and we have to find a way to solve for those relationships and incorporate those relationships in our models. And that's what we're going to learn for this particular module as well. The reason why we avoid nonlinear models is that they're extremely difficult to solve, and part of the difficulty comes from the fact that the optimal solution is not necessarily a corner point. If you recall from LP and from chapter 2, we established the fact that an LP's optimal solution is going to be in one of the corner points of the feasible region, which is not the case in a nonlinear model. So these models are difficult to solve because of this issue, and also there is sort of this uncertainty whether or not the objective function that you've solved for, whether it's a maximization objective function or a minimization objective function, you are not exactly sure if that optimization is a local optima or a global optima. I'll discuss this shortly, but this uncertainty between deciding if it's a local optima or a global optima makes it difficult to apply the results of your analysis. And also, another point to consider is that the starting point influences the solution. Generally, when we create a model template in Excel, we leave the decision variables blank and solver populates it. But even if you put fictionary values in them or starting hypothetical values in those cells, solver will replace those values with the optimal solution, and adding those values does not influence the solution. But in this case, in the case of nonlinear models, if you start the analysis with a certain starting point, or for example, instead of keeping the decision variable as blank or empty and the starting point as 0, you start at, let's say, 5, that may influence your solution, which adds to the difficulty of getting one optimal solution for your model. Now, let's talk a little more about why nonlinear programming models can be so difficult to solve. Generally, in all the examples that we've considered so far, whether it's LP, IP, or GP, the objective function and all the constraints are linear. This implies that with two variables, each equation in the model corresponds to a straight line. And in your feasible region is more of a geometric shape that you have defined boundaries for. However, when you're solving a nonlinear expression, the resulting graph is not a straight line, and can result in a curve, and the shape of the curve could be an odd shape as well. So, for example, what you see on the screen right now is a possible nonlinear model feasible region shown in this brown area here. Depending on the extent of nonlinearity in the expressions that you've used, the curve could be quite pronounced. So it might have a lot of twists and turns, which make it very complex to plot as well as solve for. Um, from chapter 2, if you recall, that whenever we graph our feasible region in a graph like this, for an LP model, the optimal solution is always at a corner point. So wherever two or more linear constraints intersect, that's where you would generally find your optimal solution. However, when one or more constraints are nonlinear, which is the case in this example here for this particular graph, an optimal solution need not be at the corner point of the feasible region. So here the optimal solution is somewhere in between. So it's not even very easy to visualize such feasible regions, just the way we've done here. This is a hypothetical situation. In real life, for a lot of nonlinear models, you can't even draw such visualizations. This is one of the major reasons why nonlinear models are so difficult to solve in practice. And it becomes even more difficult if you have more decision variables. A second reason for why nonlinear programming models are so difficult to solve is the concept of local optima versus a global optima. So perhaps a simple analogy is going to help you understand this better. A local optimal solution is like the peak of a specific mountain range, whereas the global optimal solution is the peak of the highest mountain in that range. So if you're on a specific mountain, it is likely that you only see that specific peak, whereas if you look at it from a bird's eye view and zoom out a little bit, you can see that this may not be the highest peak. In fact, the highest peak is somewhere farther away. So unless you're able to see all the mountains in the entire range from your current location, you have no way of knowing whether there's a peak higher than the current one that you've just discovered. So that's the same thing with nonlinear solutions as well. You may get an optimal solution, but it's very hard to determine if that optimal solution is a local optimal solution or there's something better out there in the range of values that you may not have considered so far. So what's the difficulty with the nonlinear programming solution is that depending on where the procedure starts, the search process could terminate either at a local optima. So for example, if I started the search process around these values here, it probably stops at this local optima A, and that's the solution that I get from my solver window. However, if I start the search process around these values, maybe my search process ends at B, and that may be the solution that I get. Whereas if I search the process around these values, then I may get a peak around here. Let's call this point Z. So depending on where the search process starts, it could terminate at either a global or a local optimal solution. And if it starts near a local optimal solution, and that's where it ends, you have no way of finding out if there is a better or a global optimal solution out there. Because there are no better solutions in the vicinity of the point that you started off at, the procedure usually just terminates and yields whatever is the nearest optimal solution to it. So, because unfortunately there's no precise way of knowing where to start the search for the NLP, um, you usually don't know whether you'll end up with a global optimal or a local optimal solution. So generally, it's usually a good idea to start try the whole solver exercise with different starting solutions for the NLP model and compare them to see which one is a local optimal and which one is a global optimal solution. Now, so far we've talked about how NLPs are going to be different from LPs and how NLP optimal solutions are more difficult to achieve, but we haven't really looked at an example of an NLP model. And so far in the semester as well, we've assumed all of our models that a typical objective function such as profit, total profit, the profit contribution per unit of each product is fixed regardless of how many units of product we make. So for example, here, let's say that we have a decision variable called y, and y denotes the number of units made of a specific product, so a table or a chair, and the profit contribution for that particular product for y is $6 per unit. So this is the profit contribution. So therefore, the total profit that you get for this would be 6y, right? However, in real life, this is extremely unlikely that the unit profit contribution of a product remains the same irrespective of what quantity of product you sell. Generally, the unit profit contribution of a product decreases as its supply increases. So suppose, for example, if instead of saying that the profit contribution per unit is $6, I tell you that the profit contribution per unit is, let me draw a line here, 6 minus 0.02y. In this case, the total profit that you get from y units of product would be equal to 6 minus 0.02y multiplied by y. And if I expand this expression, you will see that I end up with a quadratic term in my total profit expression. So if my profit contribution changes from $6 to 6 minus 0.02y, that means for every additional unit of y that I produce, my profit contribution goes down by 0.02. So if I produce 1 unit of y, my profit contribution is 5.98. If I produce 2 units of y, my profit contribution becomes 5.96, and so on. So it's decreasing with every additional unit of y that I produce. In that case, the total profit, TP, that's what it refers to, becomes 6 minus 0.02y multiplied by y, and that expands to 6y minus 0.02y squared. So now here you've achieved an objective function which has a nonlinear term y squared, which is a quadratic term, the power of 2. So this type of model we haven't considered so far. We've only considered models where we've seen just simple linear terms. So having a term which is quadratic and non-linear is something that is new to us. So that's an example of a nonlinear programming model where the objective function has this y squared in it. You could even have a nonlinear programming model where the constraints, one constraint or more than one constraints, are nonlinear. So for example, let's say if an employee takes 3 hours to complete a painting job, in a linear programming model, we would just assume that the employee takes 3 hours to complete a painting job, irrespective of how many jobs are assigned to him. But in reality, that's not the case. We know that if a person works more hours, their productivity decreases with time because they run out of energy, they get tired of doing it, they lose motivation to do something continuously, monotonously the same thing over and over again. So their productivity might decrease. So the first job that they complete might take 3 hours, but the second job that they would complete might take 3.5 hours, and the third job might take 4 hours, and so on. So that's a more realistic situation, and that's what we're trying to incorporate into our models, is having assumptions which are closer to reality than what we assume in a simple linear programming model. And that those are the kinds of problems that we're going to approach in the nonlinear models as well. In order to understand nonlinear programming models better, let's look at an example. And this example that we're going to solve for is for Pickens Memorial Hospital. Let's assume that the weekly profit at Pickens Memorial Hospital depends on the number of patients that are admitted into their three separate categories of the hospital. The first category is the medical category, the second one is surgical, and the third one is pediatric. So the hospital can admit a total of 200 patients, regardless of the category, each week. And because this hospital serves a large community, patient demand in each category is higher than the capacity of the hospital. So the details of this particular example are given in chapter 6 of the textbook. So all of the information that I'm narrating right now is directly taken from that example, which you can refer back to. So let's assume that for this particular hospital, the profit that comes per patient actually increases as you increase the number of patients who are admitted. The reason for that increase could be that the overhead costs, such as electricity, rent or lease payments, cost of the equipment, all of them remain the same. So they're fixed. So if you bring in more patients, the profit contribution of each patient increases. So we also assume that some patients who are initially classified as medical patients may be reclassified as surgical patients later on. So if a patient comes in and is taken in as a medical patient, they might be transferred to the surgical category later on, which is why you see that the profit contribution per medical patient in a linear programming model, it would have been just $45. But in this case, where we're trying to make it more realistic, it's 45 plus 2m. So for each additional medical patient, the profit contribution increases by $2. So the first patient that comes in gives you a profit contribution of 47, whereas the second patient, when they come in, the profit contribution increases to 45 plus 4, which is equal to 49. So as you see, gradually with each patient entering the hospital, the profit contribution for the medical patient increases. The same way for surgical patients. With each additional surgical patient entering the hospital, the profit contribution increases by $3. So the first surgical patient has a profit contribution of 70 plus 3, The second surgical patient has a profit contribution of 70 plus 6, and so on. And furthermore, if medical patients are transferred to the surgical patient category, then they further increase the profit contribution by $2. And the same way for pediatric patients, each additional pediatric patient increases the profit contribution of that patient in that category by $3. So the first pediatric patient gives a profit contribution of 63. The second pediatric patient gives a profit contribution of 66, and so on. Here in all of these expressions, M, S, and P refer to the number of patients in that category. Now let's further assume that Pickens Memorial Hospital has identified three main constraints for this model: the X-ray capacity, the marketing budget, and the lab capacity. The table that you see in front right now shows the relevant weekly data for these three constraints for each category of patient. The table also shows the weekly availability of each of these three resources. So the way you would read this table is that each medical patient requires one X-ray, whereas each surgical patient requires three X-ray, and each pediatric patient requires one X-ray. The same way, each medical patient has a marketing budget of $3 assigned to them. Each surgical patient has a marketing budget of $5 assigned to them, and each pediatric patient has a marketing budget of $3.5 assigned to them. And in total, you have $1,000 in your marketing budget. The same way for constraint number 3, each medical patient requires 3 lab tests, whereas each surgical patient also requires 3, and each pediatric also requires 3 lab tests per patient, and the availability is only 140 hours per week of lab tests. The hospital's chief supervisor has also noted that the time required per lab test increases as the total number of medical patients admitted increases. So based on historical data, this is how they determine the relationship, that the time required for each lab test in hours would be 0.2 plus 0.001 multiplied by the number of medical patients you have admitted in the hospital at the moment. So the higher the value of M, the more time it takes to complete a single lab test. Now let's come to the model formulation part of this example. If we are solving this problem to find out what is the maximum profit that this hospital can make given the amount of resources that they have, and how can they achieve this maximum profit, in other words, what number of medical patients, what number of surgical patients, and what number of pediatric patients would they require in order to make maximum profit, is what we're solving for this particular NLP model. So obviously we've already decided what the decision variables are going to be. They're represented by M, S, and P, where each letter represents the number of patients in that respective category. The next step is to define the objective function for our particular problem. And this is where we're going to use the profit contributions which were given 2 slides ago. So we saw from the previous previous 2 slides, that the profit contribution for each medical patient is 45 plus M. 45 plus 2M. Oh, sorry, this is a typo. This should be 45 plus 2M. Yep. And that has to be multiplied by the number of patients that the model tells us for that particular category, which is M. The same way, the profit contribution for the surgical category is 70 plus 3S plus 2M, and we multiply that profit contribution with the number of patients in the surgical unit, so that's S. So this expression gets multiplied by S plus the third term, which is coming from the pediatric unit, so the profit contribution for that which was given to us multiplied by P. So this way we end up getting an objective function which has three nonlinear terms, in fact actually four nonlinear terms in our overall expression. The first one is m square, the second one is s square, the third one is ms, and the fourth one is p square. We haven't solved for objective functions like this before, so this is the new part for us. Moving on to our constraints, the constraints are regarding the three resources that were identified earlier. Those were in terms of the X-ray capacity, the total the marketing budget that was assigned, and the lab capacity. In addition to that, earlier in the problem description, we were told that the hospital has a total patient capacity of 200 patients. So all three units, the sum of their patients should be less than or equal to 200. That's our first constraint. The second constraint is with regards to the X-ray capacity, and this is where we use the table that we saw in the previous slide, and that has to be less than or equal to 560. The same way we used the table in the previous slide to form our constraint for the marketing budget, and eventually for the last constraint, which is the lab capacity. Now, if you look at all four of these constraints, ignoring the non-negativity constraints here, the first three constraints are all linear. They're similar to what we've been looking at in LP problems. However, this fourth one is where we are going to see nonlinear terms. And the way we got to this fourth constraint, let me go into a little bit detail for that. If you look at the previous table, you saw that the number of lab tests per patient is 3 for medical, 3 for surgical, 3 for pediatric, and the total availability of lab tests is 140 hours of lab tests per week. Now, because the time that it takes to complete each lab test is given by this expression here, we have to multiply this expression with each of these three here so that we can get the total time for the left-hand side of our constraints, which is what we've done here. So the time it takes for one lab test to be completed multiplied by how many lab tests we have to do in total per week has to be less than or equal to 140. And once you expand this expression, this becomes a nonlinear inequality where you will have nonlinear terms such as m square, ms, and MP due to this multiplication process. So here we have created a full model formulation for a nonlinear programming example where the objective function is nonlinear as well as one of the constraints is also nonlinear. Now let's move to Excel to see the changes that we would need to make in our Excel template so that we can solve this as an NLP. I've switched my screen to an Excel sheet, and just for the sake of convenience, what I've done is I took a screenshot of my model formulation and added it to my Excel sheet so that I can look at the model equations and then populate my Excel template according to the same equations that I see in my model formulation. So here I would definitely recommend solving the model formulation by hand first so that you have a template like this, what you see in the form of a slide here, and then using that to transfer the terms to your Excel sheet so that you avoid making any mistakes or forgetting any terms in your model. the only thing that I've added to my Excel sheet already is my decision variables, which are the number of patients for each of the 3 units. And I've listed down my constraints here. So let's add our objective function to this Excel sheet first. If I look at my objective function in my model formulation, I can see that my objective function has linear terms such as 45m, 70s, 60p. So it has the regular linear terms here. Let me add a row here. And so I have the regular linear terms for m, s, and p. And these are simply 45 for m, 70 for s, and 60 for p. In addition to these linear terms, I have some nonlinear terms as well. And these nonlinear terms are m squared, s squared, and p squared. And in addition, we have a term ms as well. So let's do this where I put these coefficient terms in the row which says profit. So, and I'll change this to profit coefficients. And let me add, in addition to this list of regular terms that I already have, I'm going to add my nonlinear terms here as well. So m squared, I'm adding that one here. The next one is s squared. Then we have a nonlinear term called ms. And then we have the third one, or fourth one, sorry, which is p squared. Okay, so now I've covered all of the terms that are a part of my objective function, and let me put the coefficients for each of these terms in this row that I've called profit coefficients. So m squared has a coefficient of 2 in the equation, s squared has a coefficient of 3, ms has a coefficient of 2, and p squared has a coefficient of 3. So now I've added all of the coefficients, but generally what we do for calculating total profits, which we're going to do in this cell here, is we do a sum product of the coefficients row with our decision variables row, and that becomes our objective function. However, now we have a problem because our decision variables row is only containing 3 terms, whereas our coefficient coefficient row has more terms than 3, and we cannot use a sum product function if we have 2 sets of cells with different dimensions. So here, before applying the sum product function, I need to make some changes, and I need to tell Excel that there's a new row. Let's call this the variables, which are the variables in our objective function, and let's tell Excel what these variables are. The first one is m, so I'm just going to refer to the cell where m's value is being stored. The second one is s. Again, I'll refer to the cell where s's value is being stored. Then for p, the same way. For m squared, it will be the cell where m's value is stored to the power 2. The same way for s squared, it'll be C5, where s's value is stored to the power 2. For ms, it will be the cell where m is stored multiplied with the cell where s is stored. And then finally, for p squared, it'll be the cell where p is stored to the power 2. Now we have the equal number of terms in this variable row and the profit coefficients, so we can calculate our total profit as the sum product of the coefficients row with the variables row, and that will serve as our objective function. So let's put that in green, and let's call this total profits, and that's what we are maximizing for. So now that we've added our objective function, in order to remain consistent with our color coding, I want to put these cells in blue so that I remember these zeros are not coming from manually entering zeros here. Instead, they are because of the formulas that are inside these cells. So that's what this blue color is going to remind me of. Next, we're going to add each of our constraints one by one. The first constraint is the total patient capacity constraint, and the left-hand side of the equation is 1m plus 1s plus 1p. So the coefficients for m is given in this row, in this column B here. So I'll put a 1 under that, 1 under s, and 1 under p. The rest of these terms are not a part of this constraint, so I will just leave them blank, or you can put zeros here, it doesn't matter. So the left-hand side value, let's call this column LHS, would be the sum product of this whole row with the variable terms that we defined earlier. Notice that we're not using the decision variables in this case because some of our decision variables are being repeated and used in multiple terms. So we cannot add those if we just use the cells in yellow. So we have to use the whole row, which we defined as variables. So that gives us a left-hand side value of 0 for now because all of these values are 0, and that needs to be less than or equal to a right-hand side value of 200. Now let's move on to our next constraint, which is on X-ray capacity. The next constraint is the left-hand side says 1m plus 3s plus 1p. So 1 under m, 3 under s, and 1 under p. Again, the remaining terms are not in our equation, so we leave them 0. And here I can convert my equation into constant references. So I'll press F4 for the blue cells so that they can remain constant, and I can just drag this down to cover my next constraint as well. And that needs to be less than or equal to 560. The same way, let's look at our marketing budget. The marketing budget says 3M, 5S, and 3.5P. So 3 goes under M, 5 goes under S, and 3.5 goes under P. Again, the remaining terms are not in there, so I can simply drag this left-hand side formula down, and that needs to be less than or equal to 1000. Then our last and final constraint is the lab capacity constraint. For this lab capacity constraint, I would first have to expand this left-hand side of the equation, and I can do that manually by hand. So the 0.2 gets multiplied with 3m, 3s, and 3p. So it becomes 0.6m plus 0.6s plus 0.6p. The 0.01m, again, that also gets multiplied with 3m, 3s, and 3p. So that is added here as a plus sign because the original sign for 0.01m is positive, and it's also being multiplied with all positive numbers. So that becomes 0.003 because we multiply the 3 with 0.001. M squared plus 0.003 m multiplied by s, so ms, and finally 0.003 m multiplied by p. So if I look at the terms that are a part of this equation so far, our m, s, p, those three are already included in our variables. Next we have m squared, which is also there. Then we have ms, which is also there. And finally we have mp, which is not there. So I'll have to add that to my list of variables here. So let me get out of this drawing mode. And now I can add a column here where I will put the term MP because it's being used in my last constraint for lab hours, and that term is M multiplied by P. So based on the expansion of the equations that we did, the coefficient for M came out to be 0.6. For S was also 0.6, and for P it was also 0.6. For M square it was 0.003. For there was no S square in our term, so in our equation, so I'll leave that blank. There was a term for MS, and the coefficient for that was 0.003. And then finally we had a term for MP, which had, oops, let's increase the decimals here, and for MP, which had 0.003 as the coefficient. Notice that in my last equation or last constraint, there was no s squared term and there was no p squared term, so I've left those coefficients blank here. And then again, I can drag down the left-hand side formula from up top, but I have to make sure that I've included this additional column that I created, so I'm typing it manually myself. And that needs to be less than or equal to 140. So now we've added all of our constraints in here. The left-hand side values contain formulas, so I'll put them in blue, and we have filled out everything, which leads us to the solver window. So let's go to our solver window and add our inputs here. The objective function is total profits, which we need to maximize subject to changing variables. Notice that although we have these variable terms in our model, which we're using throughout, but our changing variables still remain the same three decision variables that we defined at the very beginning of the model, because Excel is using combinations of these three cells later on, and they're all given by formulas, so we don't need to incorporate all of these cells. Instead, just keeping these three as changing cells takes care of everything. And we can add one set of constraints because they all have the same sign, less than or equal to the right hand side. Okay. Check the unconstrained variables non-negative, and in the solving method you have to select the GRG nonlinear, which is the algorithm that is specific to nonlinear programming models. So far we've been using the simplex LP, but for NLP models we're going to use the GRG nonlinear, and hit solve here. And this is what the solver model tells you. It tells you that the maximum profit the hospital can make is about $118,000 by having 20 medical patients and 180 surgical patients and no pediatric patients.